Now we will study pure bending in members made of several materials. So in case we have a composite beam formed from two materials of each one characterized by modulus of elasticity E1 and E2, then in this case, we'll see that within each material, the linear variation of the normal stress will have a different slope. In fact, the normal strain will still be varying linearly with the distance y from the neutral axis. However, the slope of stress in material 1 will be different from the slope of stress in material 2. Why? Because if we consider again the pure bending deformation, so you have your beam will undergo bending, will have the formation of a certain radius of curvature characterizing the neutral axis, and we have a certain angle of bend theta. Now, in case we have, if you want, several materials or one material, we'll observe this behavior, the bending effect, and we'll be able to calculate a radius of curvature, a bend angle, and also we can use the same previous demonstration to find an expression for the normal strain. So the normal strain will still vary linearly with y for the whole section along y, and the slope will not vary, and the slope of the strain is 1 over rho. However, when you calculate the normal stress in material 1, the normal stress is modulus of elasticity of material 1 times epsilon x, which is minus E1 y over rho. However, in material 2, sigma 2 is E2 times epsilon x, which is minus E2 y over rho. So if you compare the slope of variation of stress, normal stress in material 1, it's different than the slope of variation of stress in material 2. And this will modify a little bit the analysis we have done before. We'll develop together a technique that will allow us to locate the neutral axis of this composite section and to determine our maximum stresses. So if we observe the following graphs, we'll understand what will happen in case of several materials. So as mentioned before, for the strain, we'll still observe the linear behavior from the top to bottom, and zero strain will correspond to the neutral axis level. But now we'll see together that the neutral axis for a composite section will not pass by the centroid of the composite section. Because of this, because if we study the normal stress distribution, it will have varying slopes. So in material 2, we have a certain slope, as you can see here, depending on the modulus of elasticity E2. And then suddenly when we move from one material to the other, we'll have a sudden change in slope of sigma. So we'll still have a linear variation, but with a new slope. And for this reason, the neutral axis of my system, for which the length will not change, will not be at the centroid of the composite section. And we'll see together a method that will help us to determine the location of this neutral axis. Let us find the neutral axis by going back to the physics of the problem. First, in static equilibrium conditions in pure bending, we know that the total normal force resulting from the stress distribution that is normal to the cross section should be equal to 0, because we are in the case of pure bending problem, so no net normal force, and we have just a stress distribution that will create the bending moment. So if we do force analysis, the summation of normal forces to the section is equal to 0. And the total force can be decomposed into the normal force to section 1. So normal forces to section 1 and normal forces to section 2. And to get the expression of these forces, we need to perform integration, because elementary force here, if you consider an area dA1 in material 1, then the elementary force dF1 is equal to the normal stress to which is subjected this area times dA1. So the total force F1 will be integral of dF1, integral of sigma 1 dA. And we can replace sigma 1 by its linear variation with respect to y, that is depending on the modulus of elasticity 1, the radius of curvature of the band, and of course the distance from the neutral axis. On the other hand, in section 2, we have same expression, but now with sigma 2, and we have the variation of sigma 2 will depend on the modulus of elasticity of material 2. So now, when you add these two forces and they should be equal to 0, you obtain the following expression. We obtain that in total, integral A1 minus E1 y over rho dA plus integral A2 minus E2 y over rho dA is equal to 0. Before, because we had the same material, we take E over rho into factor and we just get into the integral y dA equals 0. This is why we said before that the neutral axis should pass by the centroid of the section. However, here it's a little bit different because y is multiplied by different coefficients in the first integration and in the second integration. In order to go over this, we will develop a technique that will allow us to find the neutral axis in a simple way by just doing a small transformation for the geometry of our section. Okay, the idea is the following. We try to unify the coefficient multiplying y by changing the area considered. So instead of integrating over area dA of material 2, we say in order to have in factor a common factor which is E1 y over rho, let us define the ratio between modulus of elasticity A2 over modulus elasticity E1. And then we can replace in our equation E2 by NE1. And if we do this, will appear a common factor which is E1 over rho, and then we should do this. This is N times dA times E1 instead of E2, and instead of dealing with an area integrating over elementary area dA, we integrate over NdA, and in this way we can take into a factor outside of the integral E1 over rho. And then we get the following result, that we have the total force F is equal to minus E1 y over rho dA plus minus E1 y over rho NdA. So if you want, we can consider this is a modified area that is called, let's say, instead of A2, we are integrating now over A prime 2. And then we can take minus E1 over rho into a factor outside of the integral for the two terms. And then we'll add the other two terms and say that we are integrating over the whole area A1 plus A prime 2. Okay, we are then integrating y dA. What do we conclude then? So integral over A1 plus A prime 2 y dA times minus E1 over rho, we consider it into factor, equal to 0. This means that this integral should be 0. Therefore, the neutral axis should pass by the centroid of the modified area. Okay, let us explain again the idea. So here, all we have to do is to consider that instead of integrating over an area dA in material 2, I should integrate over a larger area if E2 over E1 larger than 1, of course. And if E2 over E1 smaller than 1, then I will integrate over a reduced area. Now, how to decide how to NdA will increase in which dimensions? Why I should increase dA along the direction parallel to the neutral axis and not in any other direction? Because I should keep same y from the neutral axis. I cannot change the distance from neutral axis because I'm integrating y dA. So y should remain the same. Just I should vary the area. I should multiply it by n. So I just multiply by n the dimensions that is parallel to the neutral axis to keep the same distance between the elementary area and the neutral axis. And then I can say that after I transform my section, instead for material 2 of having a thickness, let's say a length here b, then the length here should be n times b. And this is called the modified section. This will be the total A prime 2. And A1 will remain as it is because it's composed of material 1. So for material 1, I keep it as it is. Then I say that the neutral axis of the composite beam is equivalent to the neutral axis of the modified beam here that is made of one material. So what I did is that I did an analogy between the two type of beams. Here I have a composite beams of two material of modulus of elasticity E1 and E2. I did a modification to create a beam having one modulus of elasticity E1, having different area because A2 will be modified, but should have comparable neutral axis, same level of neutral axis. So I did a modification in a way to ensure same level of neutral axis. This means that if I determine the neutral axis for this section, it will be at the same level of the neutral axis for the composite beam. And in this way, I was able to solve the problem of a composite beam with a problem of a beam with one material by just doing an area modification. Now, we can then say, as we said, that the equation now will be simplified to integral over a certain modified area, which is A1 plus A prime 2, of integral minus E1 y over rho dA equal to 0. And we're back to the same form that we developed previously. And this means that since integral y dA is equal to y bar times total area, and this will be equal to 0, then the neutral axis should pass by the centroid of this section and not this one. Okay, so the integral of f will depend now on E1 only. Physically, it defines the summation of the normal forces resulting from the application of the normal stress on A prime made of one material. So we did a modification to have same level of neutral axis, but instead of dealing with two materials, we are dealing with just one material. Now, and as we said, since it's essential for the distance y of each element from the neutral axis to remain unchanged, the dimension parallel to the neutral axis should be changed and should be multiplied by n. So now, after we do the modification, all formulas developed before can be used. So now for this section, okay, of course, the stress distribution for this section is different than the stress distribution for the composite beam. But what I care for is that they have the same neutral axis. So I do now the analysis here, and I get, if you want, the linear distribution of stress here, but I should keep in mind that the stress distribution in the modified section is not similar to the stress distribution in the compound beam. How can I deduce back what are the stresses here? It's very simple. Okay, first, in the first material, I didn't perform any change. Okay, so if I calculate here the stress at the top level, it will be exactly the same as the stress here because I didn't modify the area. However, when I consider, for example, the bottom level, in the bottom part, I increased the area. while the force remains the same. Okay, so because we have same force, F is the same, and the area F, you know that the force is stress times area. Okay, since the area in modified section, so let me say this is A modified and this is sigma modified. Since F is the same, sigma modified times A modified is equal to sigma original in the original section of the compound beam times A original. And since A modified is equal to N times A original, I can deduce then that sigma original should be equal to N times sigma modified. Okay, so I can calculate sigma of the modified section based on the previous formulation using sigma x equal minus my over I, where I represents the inertia of the modified section about the neutral axis. And once I find this value of sigma, I keep in mind that I should go to my original beam. And because I am applying the same force, this means that because the area was multiplied by n when going from the original to the modified, okay, then I should multiply sigma modified by n to get the value of sigma original. Okay, so now this is the method, as simple as that. So whenever you have a compound beam, the first step will be to modify your cross section. For the modified cross section, you can perform the same analysis we have done before, and just you should keep in mind when calculating stresses on your composite beams, you should pay attention that sigma original is n times sigma modified. So here, this is this box is talking about what we are saying. We are saying because in the transformed section, we multiplied the area by n, and the force is the same, okay? Then the original value of sigma should be n times the value of sigma here. So if I put here sigma, here it should be n times sigma, okay? Because of the constant force, and we know that the force is area times sigma. Now, concerning the value of the radius of curvature, okay? So to determine the value of the radius of curvature, we can use the modified section also, because we have the neutral axis is at the same level for both, okay? So we can determine the level of the neutral axis by using the modified section. And then to find the radius of curvature, we use the following formula, that 1 over rho is m over E1. E1 is the modulus of elasticity of the material we are considering, because we modified the section in a way to have for the whole section one material, which is E1. And of course, the inertia I will be the inertia of the whole section relative to this neutral axis. So E1 will represent the Young modulus of, or modulus of elasticity of material 1, and I will be the moment of inertia of the transformed section with respect to its neutral axis. Let us practice on this idea by doing some problems. For example, if you consider the following problem, we have a bar having the cross-section shown has been formed by securely bonding brass and aluminum stock. So here we are using different materials in our beam. Using the data given below, determine the largest permissible bending moment when the composite bar is bent about a horizontal axis. So first, we have bending about the horizontal axis. And this means that, as I told you before, we have the vector moment then will be along this axis, okay? And then if you want to illustrate it, then you will have, it will, you can create, whenever they don't specify, so they just say it's a bending moment, a positive bending moment. This means that we are compressing the upper part, and for the lower part, we have it in tension, okay? So the neutral axis should be along the direction of the vector moment, which is the horizontal axis. And we have to find here what is the maximum possible moment to be applied to not exceed the allowable stresses. Okay. Now, in this problem, they didn't specify, they didn't, if you want, gave difference between tension and compression. So whenever they give you an allowable stress just as one value, you can consider that the limit of tension and limit of compression are equal. Okay, so you have just to determine what is the largest C to find what is the maximum stress within your system. Now, here you should pay attention that because we have two material, we should check that we are not exceeding the allowable stress in material 1 and in material 2. So to start with, whenever you have two materials, the first step will be to do transformation of your section, to modify your section, okay? Now, in general, you can determine first what is the value of N. N, as we said, is, in general, we take the largest modulus of elasticity over the smaller one. And then when we modify the area, we increase it. But you can do the opposite thing. Nothing will change. And you can define N as, let's say, E1 over E2. And then instead of increasing the depth or the length, you reduce it. Okay, so both methods will give you the same result, but by convention in general, they take N to be larger than 1 by considering the largest modulus over the smallest one, and then you will be transforming your cross section to the material of the smallest modulus of elasticity. If we check here between aluminum and brass, aluminum is characterized by the smallest modulus of elasticity. So I will consider that E1 is equal to 70 and it represents aluminum, and E2 is equal to 105 gigapascal and it represents brass. And then in this case, I will transform the whole section to aluminum material. Okay, by saying that, well, where I have aluminum, I keep the section as it is. Where I have brass, I multiply the lengths here by N. So N is equal to 105 over 70. Then instead of having for brass a length of 30 millimeter, I will extend my rectangle by multiplying 30 by 105 over 70. So the new dimension will be 30 times 105 over 70. Okay, and I do the same for the lower part here. So now I just modify the geometry of my section. It's now a beam of I geometry. Okay, so here also it's 30 times 105 over 70. And I treat it as if I have just aluminum everywhere. Okay, so now I will say that the neutral axis of my compound beam is at the same level of the neutral axis of my I-beam made of aluminum only. Okay, so now once I do this step, I will exactly use the same methodology of we did in previous problems. First, I should find the neutral axis. Here it's obvious because of symmetry. The neutral axis will just be at the middle. So no need to do any calculation because the figure is symmetrical with respect to this axis. So the neutral axis will pass by the center of the aluminum rectangle. And then this is my neutral axis. The second step will be to find the inertia I about the neutral axis we found. So we should divide here the area into, we can divide it into 3 parts. Part 1, part 2, and part 3. And as you can see, because of symmetry, I1 and I3 will be equal. And we have to use the parallel axis theorem to determine the values of I1, I3 about the neutral axis, while for the middle part, it's already, the neutral axis is already passing by the centroid. So I just have to say that inertia of part 2 with respect to the neutral axis is the formula for a rectangle, which is BH cubed over 12. So let us see in details the calculations. Okay, so as we said, the first step is to select the reference material. As I told you, you have the freedom of selecting it as aluminum or taking the other type of material here, which is brass. But in general, we consider that the reference is the material of smallest modulus of elasticity. So for aluminum, N is just equal to 1, because for aluminum, N is equal to E aluminum over E aluminum. So it's 1. Okay, why we are doing this here? In general, whenever you have just 2 materials, you just have, of course, for the reference material, you don't do any modification, and for the other material, you should multiply the area by n. Sometimes, if you have several materials, okay, then you can define n for each material. Okay, so the material of reference will have always n equal 1, and for each material you have, n will be the modulus of elasticity of this material over the modulus of elasticity of the reference material. So here for aluminum, n is 1, and for brass, n is modulus of elasticity of brass over modulus of elasticity of aluminum, which is 105 over 70 equal to 1.5. Okay, now the second step will be to calculate, if you want, the inertia of the modified section. So as you can see here, you can just put the value of n near the area to remember that I should multiply this area by 1.5. So I should multiply the dimension parallel to the neutral axis by 1.5. Okay, so as we said, so for inertia of part 1, instead of saying it's B1 H1 cube over 12, we just say that B1 should be multiplied by n. So the inertia of this part, first about an axis passing by its centroid, is N1 B1 times H1 cube over 12. Okay, this will give us the inertia about the axis passing by the centroid of this section. Since we are interested into the inertia about the neutral axis, we should apply the parallel axis theorem, and then we should do plus the area of this part, which is n1 times this area, the original area. So the original area is multiplied by n1 times d1 square, which is the distance between the axis passing by the centroid of area 1 and the neutral axis. You have the following dimensions. If we go back to the previous figure, you have 30 millimeters, 6, 30, and 6. So here, this is 6. Since this is 6, so the centroid, the axis passing by the centroid is at 3 millimeters from the top. So this distance here is 3 millimeters. And you know that since the total length is equal to as we said, we have 6 here. So 6, 30, 30. Okay. So the distance from the top to the neutral axis is 36 millimeter. And we should subtract from it the distance from the top to the neutral axis passing by the centroid of area 1, which is 3 millimeter. So we can get the distance separating, sorry, here you have this, the whole one here is 30. So this is 3, this is the value here is 6, and the value here is 15. Okay, I will just put them again. You have this distance is 6 millimeter. The whole distance here is 30, not just the distance to the neutral axis, because the whole depth of the whole length of height of this part is 30 millimeters. So we should just take the half of it. This part from here to here is 15. So from the top, the neutral axis is at a distance from the top equal to 21 millimeters. And since for the other axis passing by the centroid here, the distance from the top is 6/2, which is 3 here, 3 millimeters this part, then the distance between the two axes will just be 21 minus 3 equal to 18. So this is 18 millimeters. This is why here D1 is equal to 18. Now we can compute the value of inertia of part 1 with respect to the neutral axis, and its value is in millimeter to the power 4. As we said, due to symmetrical effect, and since you have brass in part 1 and also brass in part 3, so also at 3 should multiply by the same factor n, therefore you will get the same inertia about the neutral axis. So no need to redo the calculation for part 3. Now for part 2, as we mentioned before, already part 2 is the neutral axis is passing by the centroid of part 2. So no need to apply the parallel axis theorem. And since the reference material is aluminum, so no need to do any modification of the area here. We take it as it is. So for I2 and 2 is just 1 because aluminum is the reference material. And just we do B2H cube over 12, we get the inertia of part 2. Now we can add the 3 values, I1, I2, I3 to get the total inertia of this cross section about the neutral axis. Now, once we get I, okay, once we get I, we need to determine what is the maximum stress in aluminum and what is the maximum stress in brass, okay? First, aluminum is in this part. So you know that whenever you want to find the maximum stress, you should look at the largest distance from the neutral axis. So for aluminum, the top and bottom are equidistant from the neutral axis, and then C is equal for aluminum to 15, because we said that the whole distance here is 30, and then C is 30/2 equal to 15 millimeters. And then to calculate sigma max in aluminum, okay, we don't have to multiply by n. N is already 1. Yani if you want, n is 1. And if you multiply by n, you just get the same result. So we don't have to do any modification for aluminum. Sigma maximum in absolute value is the bending moment times C over I. Of course, I is the inertia of the modified section about the neutral axis. C, as we said, is 15 millimeter. And here we gave us the allowable stress. The allowable stress in aluminum is 100 megapascal. And what we need to find, what is the maximum moment that we can apply. So M maximum for the aluminum part is, now just pay attention for units, okay? In case you want to get your moment in Newton meter, make sure to provide C and C in meter, I in meter form, and sigma in Pascal. Okay, so M maximum is I times sigma max over C. Okay, so you just have to replace, you get the first maximum moment value, which will not allow to exceed the allowable stress in aluminum. Now for brass we should pay attention. Okay, for brass we should keep in mind that for brass we modified the geometry. So the original stress is the stress calculated in the modified section times N. Okay, so don't forget to add times N for brass. To be on the safe side, you can just always say it's N times MC over I. And for aluminum, N is 1. For brass, N is 1.5. Now for brass, okay, the value of N, as we said, is already 1.5. The value of I is the same because you have the inertia of the modified section about the neutral axis. Now, what about the value of C for brass? For brass, you have that as C1 is equal to C2. So this is C1 for brass, C1 of brass, and this is C2 of brass. Because of the symmetry, top and bottom stresses will be equal, okay, but just opposite in sign. And they said that the allowable stress for brass is 160 megapascal. They didn't give any, if you want, a difference between compression and tension. We'll see that what we should do if they give us the allowable stress for tension. For compression, we should treat them separately. Pay attention. So whenever you have allowable stresses that are different in tension and compression, then you can calculate what is the maximum M to not exceed tension, what is the maximum M to not exceed compression, and you will do the same for both materials. Then you get 4 values of M. You will select, as usual, the smallest one to be on the safe side. Okay, so now for brass, okay, we have that C, which is equal to C1 and C2 is equal to, we have seen that the distance from the neutral axis to the top and the bottom is 21 millimeters. Okay, so this is the value of C here. C equal to 21. And then we can go back to the same relation and pay attention that N is 1.5. So let us see the details of calculations in the problem to remember the steps. So as we said, first we transform the section. We calculate the inertia of the modified section about the neutral axis. Once we have I, we say that the general expression for the absolute value of sigma is absolute value of N M Y over I. So M can be computed as sigma I over NY. Now, if we go to aluminum, for aluminum, N is 1. We don't do any modification. We don't multiply by anything. We have seen that C for aluminum is equal to 30 over 2, which is 15 millimeter. They gave us the allowable stress for aluminum. We replaced to get what is the maximum bending moment that we cannot exceed to not have failure of the aluminum part. Now we redo the calculation for brass. For brass, N is 1.5. We have Y, as we said, is 21 millimeters, and sigma allowable for brass is provided. Then, as you can see, for units, as we mentioned, we provide sigma in Pascal, Y in meter, I in millimeter, in meter 4, and then we find the value of moment in a Newton meter. Now, once we calculate the value of bending moment to not exceed allowable stress in aluminum and value of bending moment to not exceed allowable stress in brass, between these two, we select the smallest because M should satisfy both conditions. M should be smaller than this value and smaller than this one. So to satisfy these conditions, we should select the smallest value. This means that the maximum bending moment that we can apply on this composite beam to avoid failure is 1.24 times 10 to the power 3 Newton meter or 1.24 kilonewton meter. Another problem. We have a copper strip characterized by a modulus of elasticity equals to 105 gigapascal, and an aluminum strip characterized by a modulus of elasticity of 75 gigapascal, which are bonded together to form the composite beam shown. Knowing that the beam is bent about a horizontal axis by a couple of moment m equals to 35 Newton meter, determine the maximum stress in the aluminum strip and the copper strip. Whenever they just say maximum stress, so I try to find the maximum value of C. My stress can be a tensile stress or compressive stress. I need the maximum in absolute value. So here we are in the case of a compound beam formed of two materials, then same methodology to follow. The first step is to select a reference material. As usual, we can consider the material of smallest E as reference. So we'll take aluminum as reference. And then for aluminum, N is 1. And for copper, N is equal to the modulus of elasticity of copper over the modulus of elasticity of aluminum. So we have N for copper is equal to 1.4. Now, this next step is to transform the section. The aluminum part will remain as it is, while for the copper part, the dimension parallel to the neutral axis will be multiplied by 1.4. Why my neutral axis is horizontal? Because they said that my beam is bent about a horizontal axis. So the couple moment vector is along a horizontal axis. And this means that my neutral axis is along this direction. And when they, as I told you, when they just say M35 positive, they consider the convention that I am compressing the upper part and I have tension for the lowest part. Now, next step is to find the inertia of the modified section. So here, I don't have symmetry like before. I should find the position of the neutral axis for the modified section. My modified section will be in this form. So to find its neutral axis, I should use the method that y bar is equal to summation of yiai over a total. Okay, this is what I will do now. I will consider two areas. I will draw a table. Now here, keep in mind to use modified areas. So you can, from the beginning, say I will multiply this dimension by n, or if you want, you can calculate the original area and then make a column for n times a. For aluminum, it will remain as it is. For copper, you will multiply by 1.4, which is the ratio of modulus of elasticity of copper over modulus of elasticity of aluminum. And then this is the column you will use now because you will work on the modified section. Now for each section you determine y bar for part 1. So if we go back to the previous figure to determine y bar for each of the areas, you take the bottom, you can take the bottom as the reference. Y bar for the copper part is 1.5 millimeter. And y bar for the aluminum part is 3 plus 4.5 is 7.5. And now once I determine the centroid of each of the two parts, keep in mind that we change the dimension in a way to have the same y bar, okay? This is why when we did the modification, we always say we increase the length parallel to the neutral axis to not affect y distances. Y distances should remain the same, to have the same position of the neutral axis. So as we said, for area 1, we have y bar is 7.5 millimeter. For area 2, y bar is 1.5. Then we can compute NA, which is the modified area, times y0, okay, for each part. So now we get n times a times y bar 0 for each part, and then we can do the summation. And in this way, to find the position of centroid of the modified section, we divide this term by this term, okay? And this will give us what is the position of the neutral axis. So we deduce that the neutral axis is 5.59 millimeter above the bottom line. And once we specify this, we need to determine the distances between the neutral axis and the axis passing by the centroid of the two parts, A1 and area 1 and area 2. You have that for area 1, n times area 1, n times area 2 if you want, after multiplying by n. The centroid will remain in the same location because we modified the dimension parallel to the neutral axis. We said that the centroid is at a distance of 1.5 millimeter from the bottom. However, for the neutral axis, we found out what is the distance from the bottom, which is 5.59. Okay, so we just do the difference, 5.59 minus 1.5. We get the distance between the axis passing by centroid of area 2 and the neutral axis. And now for aluminum, we have we said that the position of y is at 7.5 millimeter from the bottom line. So the distance from the axis passing by the centroid of the aluminum part to the neutral axis is this one, which is 7.5 minus 5.59. Okay, so now you determined the distances d1 and d2, and then you are ready to find your inertias. Okay, you apply the parallel axis theorem. For part 1, the aluminum part, N1 is 1 because it's the reference material, so you do B1 H1 cube over 12. This will give you the inertia about the axis passing by the centroid of this area, plus N1 A1 D1 square to do the parallel axis theorem and find the inertia about the neutral axis. We do the same for the second part, and we should keep in mind that N2 for the second part, we did a modification. N2 is equal to 1.4. So we replace N2 by its value. And we have that inertia is N2B2H cube over 12. And to have the inertia about neutral axis, we do the parallel axis theorem. And now, once we get a I1, I2, the total inertia can be calculated as I1 plus I2. Since all dimensions used are in millimeter, first you get the result in millimeter 4. Don't forget to convert into meter 4 to use at the end your SI units. Now, once we find the value of I, the question is to determine what are the maximum stresses in aluminum and maximum stress in copper. Okay, to be able to determine in aluminum what is the maximum normal stress, we should determine what is C, what is the maximum, the farthest distance from neutral axis to any point in aluminum section. So we already said that the neutral axis is at a distance of 5.59 from the bottom. Okay, so now we should determine C1 and C2 for aluminum. C1 and C2 and determine which one is largest. Okay, you have that C1 is equal to the difference between this distance, so the whole distance here, which is 12 minus 5.59. So C1 is 12 minus 5.59. This is C1 aluminum. C2 aluminum is equal to this distance. This distance is 5.59 minus 3, which is 2.59. So of course, C1 is larger. So I will take this value of C as maximum distance from the neutral axis to compute what is sigma in aluminum. So sigma max in aluminum in absolute value. Here it's a compression stress if we consider that M is positive. So the absolute value of sigma maximum is for N is 1 for aluminum, it's the reference material. So M times C, which is 12 minus 5.59 in millimeter, I convert it to meter, over I, which is the inertia of the modified section above the neutral axis. Now for copper, I should pay attention to multiple, that N is not 1 for copper. So now for copper, I multiply by N. Okay, N is the ratio of 105 over 75.